Hello, welcome to Engineer's Mindset. Now let's consider this question in three dimensions, which says if cable AD is tightened by a thumb and develops a tension of 1,300 pounds, determine the tension developed in cable AB and AC and the force acting and the force developed along the antenna tower AE at point A. Okay, so this is the antenna tower and these are the tension, these are the cables, okay, at different points B, C, and then point D. And the question says if you determine the tension in cable AB and AC. We are given tension in cable AD. Tension in cable AD was given to us, so we are now defining tension in cable AC and AD. We were also given that determine the force developed along the antenna tower AE at point A. So which means there's a force at point A. So we don't know that force, we also have to find the force. Now, before we can be able to solve this problem, the first thing to do is to outline the free body diagram. So the free body diagram will help us to actually solve the problem, but we can as well still solve the problem from the diagram itself. So let's just present everything here at once. Okay? Now, this is my y-axis, we will give the equation. We also have this to be my x-axis, and this is actually our z-axis. Now, there's a tension in cable AB, so let's represent the tension. This is tension in cable AB, so simply call this CAB, and for given, it has a value. There's also a tension in this cable AB. There's also a tension in this cable AD, so okay, let's call this TAB. Okay, let's put it somewhere here. Tension in cable AD. Okay, there's also a tension in this cable AC, so let's call this tension in cable AC. Okay, for this man here. Alright, now the first thing to do is what? Pick out the positions. Remember, my z direction is actually what? My k, and then my y direction is actually my j. My x direction is also what? My I. Okay, so this is the positive direction from the origin. If any force component moves towards this direction, it is the positive direction of x. So that's positive I. Okay, but if the force component moves backward, then it's going to be negative I. Okay, this is negative I. Same thing happens there. Any force component that moves from the origin in this direction is positive j. So if the force component moves backwards, this is going to give me negative j, okay, minus j. Also, upward is actually positive k. If the force component actually comes downwards, okay, downwards, this is going to give me negative k. Alright. Now, the first thing to do is to obtain the position vector. Okay. First thing to do is to obtain the position vectors. Okay. Obtain the position vectors of each of the forces, okay, of each of the tensions. Obtain the position vector for each of the tensions. Okay, so we have different positions now. Let's move from the origin. The way to obtain a position vector is simply move from the origin and locate all the points. Point E here is the origin, so we move from the origin to locate all the points. Now, point A, also, we were given that there is a force along the antenna tower AE at point A. So we don't know the force. Let's also call that force P. Since it's along the tower, which means the force is vertical, it's going to be vertical force because it said it is along the tower AE. So let's simply call that force P. Now, you can decide to choose vertically upward force as P. Okay, this is the force P. You can try to also choose this force to be acting downwards. You will not be wrong. At the end of the day, if you choose the force and you obtain negative value from the force, it only means that the direction you assumed was wrong. Because you don't know this force, you have to assume the direction for it. So I will simply assume that this force that's acting along the antenna tower AE is actually what? Pointing upwards. Now, if I choose the force to be pointing downwards, it doesn't also matter. But at the end of the day, if the answer has a negative value, it now means that the direction I assumed was wrong, but not the answer. The answer will forever remain correct. So this happens to now be what is called my free body diagram. After the free body diagram, the next thing to do is simply what? Obtain the position vectors. Okay? Okay, obtain the position vector. That is simply obtain the position of all the first components that you have there. That's simply obtain the position of all the first components that you have there. So you move from the origin to locate all the points. If I move from the origin to locate point A, I will simply move from origin moving upwards. And if I'm going upwards, I said it's actually what? This is the Z direction, which is K. So moving upwards is actually what? Positive direction, which is positive direction of K. And the distance covered is simply what? This height, given here as 30 feet. So therefore, position of A, simply called as RA, is simply what? 30 K. Also, locate the position of point B. Also, locate the position of point B. So move from the origin to locate point B. Now, this is where point B lies. Point B is actually two-dimensional, which means I have to go in axis to locate point B. So first of all, I will move from the origin to this point. Notice that I have covered this distance, which is what's given as 10 feet, and I move in the positive x direction, which is also arrow. So moving this way to this point, I have covered 10 feet in the positive x direction. And then again, I will move from here to this point to locate point B. From this point to this point is actually 15 feet, and it's towards what? The negative j direction, because this line is the y direction, which is j. So going backwards is actually what? Minus j. So I move from point O, the origin, that's point E, down to this point, covering this height 10 feet. Okay, covering this height 10 feet. Okay, then I move from this point. Okay, move from this point to locate point B, which is what? Negative the direction of j. So I'll simply have plus 10. That's okay, plus 10 in the I direction, and then plus 10 in the I direction, and then minus 15 in the j direction. So I'll simply have plus 10I minus 15j. Okay, that's the position of force B, or the tension in cable B. Also, we'll locate the position of tension cable C. To locate cable C, move from the origin to this point. Notice that you're moving against the I direction, negative in the I direction. Move from the origin down to this point first, negative in the I direction, and you cover this distance 15 feet. So that should be minus 15I. Then you move from this point to locate point C, also moving backwards to the I direction. You move from this point to locate point C, you're moving backwards to the I direction, which is what? Minus 10 J. Okay, so you have minus 15 going from the origin to this point, going backwards, that's minus 15, which is this distance, minus 15I. So RC is actually minus 15I. Okay, and then at this point, you also move backward to point C, covering this distance 10 feet backwards, so it's negative J, minus 10J. Okay, so that's the position of point C. Finally, let's find the position of force tension for the cable D. To locate cable D lies directly on the y-axis. It lies directly on the y-axis, so simply move from the origin to this point, covering what this distance, 12.5 feet. Simply from the origin to this point, it lies directly on the y-axis. So moving from the origin to this point, we cover 12.5 feet. Remember, it goes in the positive direction, so it is positive. So you have 12.5 feet in J direction. So RD is actually 12.5 J. So this becomes your position. Now, after the position, okay, you now find the position of each of the cables with one another. Okay. Alright, so all the cables are all fixed at point A. Take note, the entire cables, 3 cables, TAB, TAC, and TAD are all fixed at point A. So point A becomes what? The reference vector. Okay, point A becomes the reference vector. To now find the position between A and B, to find the position vector between A and B, you simply have arrow AB, and arrow AB simply was arrow B minus arrow A. Okay, so arrow A remains the reference vector. So every other vector moves to locate what? Point A. Okay, so RA becomes RB minus RA. Therefore, RAB is now equal to RB gave us 10 I minus 15J. So you simply have 10I minus 15J. Okay, so we said minus RA. RA actually gave us what? 30K. So this is minus 30K. So this is the position of force A and B. Okay, since all the cables are tied to A becomes the reference point. So we move from the other cables, all the other cables to all the other points to locate point A. Now, after obtaining the position vector between A and B, next thing to find is magnitude of the position vector. So you simply find magnitude of A, B. Okay, and that magnitude is simply what? The square root of the square of the individual terms. Sum them up. Take the square root and then take the square of the individual term, then add them up. So you simply have this. This is 10 squared plus you have this minus 15 squared plus you have this minus 30 squared. That becomes the magnitude. So RAB magnitude is now equal to 10 squared is actually 100 plus 15 squared should be 15 squared is 225 plus 30 squared is 900. Okay, so if you add them all together, so we simply have that magnitude of AB is equal to the square root of 1225. Okay, therefore the magnitude of that position vector is simply equal to what? You have 35. So this becomes the magnitude of the position vector. Alright guys, so I'm going to move these positions now over here so that I'll make space for myself on the board. Because the calculation is actually long. I'll move these positions over here. Okay? Alright, so after obtaining the magnitude of the position vector, the next thing to do is to obtain the unit vector. Okay, so we'll find unit vector of what in table AB. Alright, so unit vector we use lambda to signify unit vector. So lambda AB simply means the position vector of cable AB all over the magnitude of cable AB. Okay, this becomes the unit vector. Okay, so position vector of cable AB, we've already found out to be this, which is 10I minus 15J minus 30K. So you simply have 10I minus 15J minus 30K. Okay, all over magnitude gave us 35. So all over 35. Now this is something I'm saying lambda AB is equal to, we simply have 10I all over 35 minus 15J all over 35 minus 30K all over 35. Therefore, the unit vector in cable AB is now equal to, so 10 divided by 35, that gives us 0.29 I minus 15 divided by 35, that gives us 0.43 J minus 30 divided by 35, 0.86 K. Okay, so this becomes the unit vector in that cable. Now, the position vector, after obtaining the unit vectors, next thing to find is the position vector of tension in cable AB. And the formula for it is simply this. Position vector of the tension AB, okay, is simply the magnitude of the tension in cable AB times the unit vectors in cable AB. This is all you have. And that's it. Okay, so we simply have tension in cable AB. Since we don't know the magnitude, it wasn't given, it's part of what we're looking for. Okay, so this simply multiplied by unit vectors. The unit vector will have 0.21I, 29I, 0.29I minus 0.43J, okay, and minus 0.86K. Alright, so if you expand this bracket now with TAB, we are going to have that the position vector of tension in cable AB is now equal to, expand with TAB, you have 0.29 TABI, okay, minus 0.43 TABJ, okay, minus 0.86 TAB. Okay, alright, so let's keep this equation aside. Let's call this equation 1. Okay, let's call this equation 1. We are going to be reading this letter. Now, what was done for this cable AB, we will do the same process for other cables, for cable AC and AD. Okay? Alright, so I said since the cables are tied at point A, it means point A remains the reference cable. So we'll move from every other point to point A. So we've done for cable A, B. Let's now do for cable C or AC. So we'll simply call that, we have to now find the position vector between cable A and cable C. And that position vector is simply RAC. And RAC is simply, since A is reference point, it will always remain RC minus RA. So we always subtract RA from all of them because RA remains the reference vector. Okay, so we got RC is equal to minus 15I minus 10J. So this is actually what? Minus 15I minus 10J and then minus RA. RA gives us 30K. So minus 30K. Alright. So therefore RAC, position vector between A and C is actually minus 15I minus 10J minus 30K. Okay, so having done this, after the position vector between the two cables, next thing to find is magnitude of position vector. So we'll simply find RAC magnitude, and that's equal to the square root of, okay, so we have 15 minus 15 squared plus minus 10 squared plus minus 30 squared. Okay, so we have this RAC magnitude is actually equal to the square root of minus 15 squared becomes 225. Please take note, the square of a negative sign becomes positive. Okay, plus minus 10 squared becomes 100 plus minus 30 squared becomes 900. And this is actually the square root of 1125. Therefore, the magnitude of the position vector AC is actually equal to 35. So after obtaining the magnitude, I said the next thing to do is to what? Find the unit vectors. So we find unit vector in cable AC. As usual, unit vectors we use lambda to represent it, and that's equal to position vector of cable AC all over magnitude of cable position vector of cable AC. And that's equal to the position vector of cable AC, we had minus 15I minus 10J, okay, and then minus 30K. Alright, all over the magnitude gave us 35, all over 35. Okay, so the unit vector in cable AC is now equal to so I said you can simply break this to be simply minus 15I divided by 35 minus 10J divides 35 and then minus 30K divides 35. So we are going to obtain the unit vector in cable AC as simply minus 15 divided by 35. That is minus 0.43 I, okay, minus 10 divided by 35, minus 0.29 J, finally minus 30 divided by 35, minus 0.86 K. Okay, so I said after obtaining the unit vectors, the next thing to do now is to what? Find the position vector of tension in cable AC. So we'll also do that. Alright, so the position vector of tension in cable AC is simply TAC position equal to magnitude of tension in cable AC multiplied by lambda unit vector of cable AC. And this is now equal to the magnitude of tension in cable AC multiplied by the unit vector of that position is simply given as this minus 0.43i. So we have minus 0.43i, okay, minus 0.29j, 0.29j, minus 0.86k. Okay, so you have this. So let's simply expand the bracket and see. So therefore, the position vector of tension in AC is now equal to, so we use TAC to expand the bracket. We simply have minus 0.43 TAC I minus 0.29 TAC J, and finally minus 0.86 TAC. Okay, so let's call this equation 2. Okay. Alright guys, let me take this equation 1 up. Let me take it up. Equation 1 is TAB 0.29 TABI minus 0.43 TAB G minus 0.86 TAB. Call this equation. Okay, so I just took equation 1 up so I can take it off here. Alright, so after obtaining this position for cable AB and cable AC, let's also find it for cable AD, which is the final cable now. Alright, so it's still the same procedures. First of all, find the position vector between RA, cable A, and cable D, and that's simply RAD. And that's simply RAD. And RAD is given as, I simply say RD minus RA. Always, since A is the reference vector, always subtract A from other position. So RD gave us 12.5J. So we simply have this equal to. So we have 12.5J minus RA minus RA, and RA is 30K. So minus 30K. So you have this. So if this is the position vector, next is to find the magnitude of position vector in table AD, and that's simply the square root of the sum of the squares of the individual terms. So we have 12.5 all squared plus minus 30 all squared. Okay, this is equal to RAD magnitude is equal to the square root of 12.5 squared. That's 156.25 plus, again, minus 30 squared becomes positive, negative square is positive. So 1 plus 900. So this is equal to the square root of 1056.25. Okay, so the square root of that value will be RAD magnitude is simply 32.5. Okay, so after obtaining the magnitude, the next thing to do is to obtain the unit vectors. Okay, so lambda AD is simply the position vector of AD all over the magnitude of the position vector of AD, and that's equal to the position vector of AD was given as 12.5K, so you have 12.5J minus 30K all over magnitude, which is 32.5. Okay, so you have this, and I said you can also break this equation to lambda AD is now equal to, this can be written as 12.5J divided by 32.5, okay, minus 30K divided 32.5. Okay, so to do this, we are going to obtain a value for the unit vector in cable AD to be. So let's start. 12.5 divides 32.5. That gives us 0.38J minus 30 divided 32.5. That gives us 0.92K. Okay, so having done this, you now look for the next thing to do is to look for the position vector of what? The tension in cable AD. So you simply have tension in cable AD to be equal to the position vector of tension in cable AD to be equal to the magnitude of the tension in cable AD, okay, multiplied by unit vectors in cable AD. So this is equal to, now from the question, it was given that the tension in cable AD is actually what? Actually 1,300 pounds. Okay, so we are given tension in cable AD. CAD was given as 1,300 pounds. It was given as 1,300 pounds. So simply, in place of the magnitude of tension, we simply have 1,300 pounds multiplied by the unit vector of that tension. Okay, the unit vector of the position is simply 0.38J. So we have 0.38J, okay, minus we have 0.92K minus 0.92K. Okay, so for cable AD, the tension was given to us, so we have to put the tension into what? The formula. So in place of the magnitude of the tension TAD, we simply put 1,300 pounds, okay, multiplied by the unit vector. So to expand the bracket, I will have tension in cable AD is now, position vector of tension in cable AD is now equal to, so 1,300 multiplied by 0.38 gives us 494 in the J direction, okay, minus 1,300 multiplied by 0.92 gives us 1196K. Okay, so you can call this equation 3. Okay, so equation 1, equation 2, and equation 3 shows us the position vector of the entire tension acting on what? The system, on this cable. It shows us the position vector of the entire force or tension acting on the cable. So what we'll do at this point now is simply employ equilibrium law, sum the entire tension force together and equate it to 0. So for this system to be in equilibrium, the total force acting on the system must be equal to 0. So we'll sum them up and equate it to 0. Okay. Alright, so first of all, let's now get the total force acting on the system. Summation of force is equal to, first we have tension in cable AB, which is tension in cable AB plus position vector of tension in cable AC plus position vector of tension in cable AB. Not also forgetting that there was a force acting from the cushion along the antenna line. We choose that force to be what? P, and it is pointing upward. So if it is pointing upwards in the direction of C, so which means we assume that it's going to have a positive value. So you're simply going to have plus that force P in the K direction. This is the solution of the entire force acting on the system. Now, from equilibrium law, okay, we simply say that summation of this force is equal to what? 0. For the whole system to be in equilibrium, the sum of the entire force will be equal to 0. That simply means now that tension in cable AB plus tension in cable AC plus tension in cable AG plus PK must be equal to 0. So we'll not bring in these tensions. Now, from equation 1, we have tension equal AB, which is this. So we'll bring the values of this tension now into the formula. So we have 0.29 TAD for TAD, we have 0.29 TAD okay, minus 0.43 minus 0.43 TAD minus 0.86 TAB K. Okay, so that is the first tension for TAB. So we add this. So we add this to tension, position vector of tension equal to AC. So plus position vector of tension equal to AC. That gives us that's equation 2, which is this minus 0.43 TACI. So we have minus 0.43 TACI, okay, minus 0.29 TACJ, minus 0.29 TACJ, and finally we have minus 0.86 TACK, minus 0.86 TACK, okay. So we have that, and then we also add up what tension equal to AD. So plus tension equal to AD gave us 494J minus 494J, yes, minus 1196K. So we have 494J minus 1196K. Okay? Alright. And then finally we have plus PK, which is this force here, plus PK. So plus P, and the whole of this is actually what? 0 from every number. Sum the entire force acting on the system and equate it to 0. Okay, so if we have this now, this is what we'll do. At this point, we now collect what? Like terms in unit vectors. We collect like terms in unit vectors. So bring all unit vectors that look alike together. So you bring I to I, J to J, and K to K. So we simply have I, J, and K. So we'll add all the unit vectors, we'll collect like terms in unit vectors. Let's do that now and see what we're going to have. So here, I have 0.29 TAB in the I direction, and then I have minus 0.43 TAC also in the I direction. So it means I can add all these two. Okay, so I will simply have 0.29 TAB, okay, minus 0.43 TAC, all is in the I direction. So bring all the unit vectors together, like terms of unit vectors. So I to I, J to J. Okay, next we have minus 0.43 TABJ. I also have minus 0.29 TACJ. I also have 494J. So I can add all of them together, all the J times together. So I will simply have minus 0.29 TAC minus 0.29 TAC in the J direction. We have minus 0.43 TAB in the J direction. So we have minus 0.43 TAB in the J direction. Okay. We also have minus 0.29 TACJ minus 0.29 TAC in the J direction. Finally, we have plus 494 in the J direction. So plus 494. This is in the J direction. So we have this. And then we add up all the K times. Okay, so we have minus 0.86 TABK. We have minus 0.86 TACK. We also have minus 1196K. We also have plus PK. So add all the K times together. We simply have plus, okay, minus 0.86 TABK minus 0.86 TAB. Okay, we also have minus 0.86 TAC, okay, minus 0.86 TAC in the K direction. We also have minus 1196K. So this is minus 1196K. And then we have plus PK. So plus P, okay, plus P all into K. The whole of this is equal to 0 from equilibrium condition. So all we did here simply was collect like terms in unit vector. So we bring all the i's together, all the j's together, and all the k's together. Okay, so when we get to this point now, we now have to employ another form of equilibrium equation, because this equation now looks like me saying summation of force in the x-axis, summation f of xi, plus summation of force in the y-axis, summation f of yj, plus summation of force in the z-axis, summation f of zk, being equal to 0. This is what this equation now looks like. I sum all the force in the I direction, this is it, all the force in the I, sum all the force in the j direction, and then sum all the force in the k direction and equate to 0. This is the equilibrium equation. This is how we can present what it is. So this means summation of the entire force in the x-axis I, summation of the entire force in the y, j, summation of the entire force in the z, k, and this is equal to 0. Now, for this law to be true, it simply implies that summation f of x in the I-axis must be equal to 0. Also, summation f of y in the j-axis must also be equal to 0. And summation f of z in the k-axis must also be equal to 0 for this law to be true. So which means all the forces in the pointing towards the I direction equate to 0. All the force pointing towards the j direction equate them to 0. All the force pointing towards the k direction equate them to 0. Then this law cannot be true. So if that's the case, then we start with the summation f of x equals to 0. So let's sum all the force in the I direction to 0. So we simply have 0.290 AB minus 0.420 AC equals to 0. This will give us 0.29 TAB minus 0.43 TAC equals to 0. Call this equation 4. Call this equation 4. Next, summation of force in the y-axis or j equal to 0. So we sum all the force in the j direction and equate them to 0. So we have minus 0.43 TAB, okay, minus 0.43 TAB, okay, minus 0.29 TAC, minus 0.29 TAC, okay, plus 494 plus 494 equals 0. Call this equation 5. Also, the last summation of force in the z, which is k, equals 0. Okay, so we sum all the force in the k direction and equate them to 0. So we have minus 0.86 TAB, okay, so we have minus 0.86 TAB minus 0.86 TAG, okay, TAC minus 1196 plus P equals 0. So call this equation 6. Okay, so you're here at the 6th equation. At this point now, everything becomes easier for us to solve. Okay, so we can consider from equation 1. Okay, so notice now that equation 4 and equation 5 can be solved simultaneously, because there is no other unknown. Two of them have different same unknown, TAB, TAC, and TAC. So we can solve these two equations, 4 and 5, simultaneously to obtain the values of A, B, and AC, so that we can find the value of this for P. So let's start with equation 4. From equation 4, we have that 0.290 AB, okay, minus 0.480 AC is equal to 0. So let's send minus 0.480 AC over to this side of the equation, I will simply have 0.29 TAB will be equal to negative sign positive and equal sign becomes positive. I have 0.43 TAC. Okay, so to make TA the subject, divide both sides by what? 0.29. So I'll simply have that TAB is actually equal to 0.43 divided by 0.29 TAC. Okay, so this will give us a value for TAB. So 0.43 divided by 0.29. Alright, so from here, 0.43 divided by 0.29 simply gives us that TAB is actually what? 1.48 TAC. So we call this equation 7. So at this point, simply substitute equation 7 into equation 5. Okay, because we are solving these two simultaneously since they are easier. Okay, so we are solving the problem simultaneously. So substitute the value of what TAB into equation 5. So wherever I see TAB in this equation, I will simply replace it with that value for TAB. Okay, so equation 5 actually gave us from 5 we have minus 0.23 TAB and minus 0.29 TAC minus 0.29 TAC, okay, plus 494 equals 0. Alright, so in place of TAB now, that means here we simply put minus 0.23 in place of this TAB now. We put in this value 1.48 TAC, okay, minus 0.29 TAC plus 494 equals 0. So let's expand this now. Minus 0.23 multiplies 1.48. That's minus 0.34 TAC minus 0.29 TAC plus 494 equals 0. So at this point now, we can find this value because they are all the same term. So minus 0.34 minus 0.29. So that gives us minus 0.63 TAC, okay, plus 494 equals 0. So let's send minus 0.63 TAC over to the side of the equation. Negative sign plus and equal sign becomes positive. So I'll simply have 494 is now equal to this is 0.63 TAC. Therefore, to find the tension in the AC, divide both sides by 0.23. So that simply implies that tension in the AC is simply what? 494 divided 0.23. And that implies that TAC is equal to 494 divided 0.63. Okay? So that simply implies that TAC is now equal to 784.12 pounds. So you can simply approximate TAC. Tension in the AC will be actually equal to 784 pounds. Okay? This becomes the value of tension in the AC. Now, having no tension in the AC, all we need to do is what? Simply substitute that into what? Equation 7 to obtain tension in the AB. Alright, so substitute TAC into equation 7. Now, equation 7 gives us TAB is now equal to, we have 1.48. Okay, so in place of TAC, we actually put in 784. So times 784. That gives us the value of the tension in cable AB, and that's equal to 1.48 times 784. That's 1168.3 pounds. So we can actually approximate this to mean that tension in cable AB is actually 1168 pounds. Okay, so we'll have it to be tension in cable AB. So we now know tension in cable AC, we know tension in cable AB. All we need to do is to what? Simply plug in those values of tension into what? Equation 6. So in place of AB, in place of AC, then we can now find the value of the force P. That's the force that governs around the antenna. Okay? Okay, so we have now that. Alright, so substitute TAB and TAC into equation 6. Okay, into equation 6, now we can find the value of force, that force P. Alright, so from this 6 we have minus 0.86 in place of TAB. TAB actually gave us 1168, so we have 1168. Okay, minus 0.86 TAC. TAC gave us 784. Okay, 784. Okay, minus 1196 plus P equals 0. Okay, so let's now expand the bracket and see. We have 0.86 multiplied by 1168. So that is minus 1004.8. Okay, minus 0.86 multiplied by 784. We have minus 674.24. Okay, so minus 1196 plus P equals 0. So we can now evaluate all this together. Minus 1004.8 minus 674.24 minus 1196 minus 2875.04. Okay, plus P equals 0. So let's send minus 2875.04 over to the side of the equation. Negative sign plus and equal sign becomes positive. So it now means that the value of P itself is now equal to, so we simply send minus 2875.04 over here, it becomes positive. 2875.04 pounds. So we can simply convert this to P equals to 2875 pounds. Okay? Alright guys, so that's how you obtain the tension in those cables, cable AB, AC, and then the force at the point A. I hope you enjoyed this video. Please do well to like, share your thoughts in the comment section. Of course, subscribe to the channel and invite your friends for more subscribers. I will see you in the next video with another wonderful question on 3-dimensional spatial forces. Thanks.